Hi there. So we're moving from the structure of a nucleus to what happens when nuclei become too big for themselves, and that's radioactive decay. So nuclei that emit particles and energy are radioactive. That's the definition of radioactive. And material that emits particles and energy can also be called decay, right? So rather using the term radioactive, radioactive decay, a decay of some type is nucleus emitting particles and energy, or a substance that's emitting particles and energy. Nuclei decay from a less stable form to a more stable form. So they're trying to get small enough for that strong nuclear force to hook them together. And it's important to note that radioactivity, although the name is a bit upsetting to some of us, is a natural process. It's certainly a process that people have messed with here and there through science and engineering, but it's a natural process. So there are three types of radioactive decay, three types of radiation: alpha decay, beta decay, and positron emission, or gamma decay. The emission of an alpha particle from a nucleus is a process called alpha decay. And an alpha particle is a different name for a helium nucleus. An alpha particle is made up of 2 protons and 2 neutrons. So if a nucleus gets too big and the strong nuclear force can't keep it together, can't fight against the repulsion of the positively charged protons, the protons get kicked out, right? Some of the extra protons get kicked out. And what gets kicked out is a helium nucleus, 2 protons, 2 neutrons, relatively stable configuration. And if you're kicking out 4 nucleons, 4 particles, that means you decrease your mass number, total particles, by 4. So your new nucleus has 4 less nucleons. And if you're kicking out 2 protons, then you're going to decrease your mass number, your atomic number by 2, because you've lost 2 protons. So that means that it's now a new element, right? You've changed the number of protons, so you've changed the properties of the element. In the case of this picture, we have uranium-238 decaying into thorium-234 plus an alpha particle. That's the story. Option 2 is beta decay. So beta decay occurs when a neutron is changed into a proton. Excuse me, what? Or a proton changes to a neutron inside of the nucleus. That's too cool for school, right? So in a beta decay, a neutron changes into a proton. That is, a neutral neutron changes into a positively charged proton. This can happen, according to quantum mechanics, because quarks and gluons can mix and mingle and kind of exchange with each other. So a neutron is 2 down and 1 up, and a proton is 2 up and 1 down quark. So if a neutron changes into a proton, one of those down quarks switches to an up quark. It's like magic to me. So when that happens, however, both mass and charge have to be conserved. So the neutral neutron changed into a positively charged proton, which means there must be in the mix now a negatively charged particle so that the net charge doesn't change. We call that negatively charged particle a beta particle. It was measured and noticed before we understood electrons, protons, all that jazz. So in beta decay, the neutron changes into a proton, and a beta particle, which is an electron, and an antineutrino are ejected from the nucleus. You've now changed one of your neutrons to a proton, which means you've increased your atomic number by 1. You have now a different substance as a result of this decay. And sometimes it's energetic enough to also eject a gamma particle, which is the same thing as a high energy photon. Okay, so the third option is positron emission. I'm not sure why this is here. Let's move it out of the way. Positron emission occurs in the reverse, right? So if a neutron can switch to a proton because quarks are interchangeable in some way, then the opposite should be able to occur as well. A proton switches to a neutron. So one of the up quarks in the proton switches to a down quark in an exchange in gluons and quirkiness inside of the proton. That's positron emission. So the reason it's positron emission is that proton, which is positively charged, switched to a neutral particle. So for a charge to be conserved,